Hello everyone and welcome to the channel. In this video, we'll continue looking at the read and write pulses, and specifically, we'll improve the write timing by generating a new clock phase that is shifted to the left of the clock. So that's going to be pretty exciting. So I hope you enjoy. Okay, so in the past video, we've been building this new logic circuit for the read and the write pulse. And we have shown in the timing diagram of the RAM in a write cycle that this circuit is too slow. It takes around 25 nanoseconds to propagate, and we want the write pulse to happen before 10 nanoseconds after the falling edge of the clock. So that's too slow. So the solution I'm going to implement is we're going to shift this write pulse to the left using a new clock phase that happens before the clock. So we've been using this clock plus phase, which is shifted to the right by 10 nanoseconds. And what I'm going to do in this video is generate a clock minus that is shifted to the left of the clock. So the transitions happen before the transitions of the clock. And then if we feed that new phase into the write pulse, we're going to be able to have it trigger at the right moment. So let's go into KiCad and see how we're going to do this. So the way we've been generating this new phase until now was by using this DS1035-10, which is a 10 nanosecond precise delay line. And in a single package, we have 3 of them. So what if we take the 3 of them and chain them? If we input a clock signal, we're going to get out 3 phases, and the one in the middle is going to be the clock. The one on the right is going to be our clock plus signal. And here I'm going to call this clock minus, which is the clock shifted to the left by 10 nanoseconds. Let's look at the datasheet of the DS1035 so we can see what it looks like in terms of timing. So here is the datasheet of the DS1035, and you can see that the -10 version I'm using has a 10 nanosecond delay per output, and the tolerance of this timing is plus or minus 1 nanoseconds at room temperature, and it can vary by an additional plus or minus 1 nanoseconds over temperature and voltage. So all in all, it's plus or minus 2.5 nanoseconds per delay. So let's build a timing diagram of this new circuit, and we can see how it looks like. So this is the timing diagram of our new circuit. If we take the input clock as a reference, each additional hop will delay the signal by 10 nanoseconds plus or minus 2.5. And so as we go through the hops, the uncertainty gets increased. Each step adds 2.5 nanoseconds of uncertainty, meaning that compared to the clock input signal, clock plus gets delayed by 30 nanoseconds plus or minus 7.5. Now there is another way to look at this timing diagram. If we now take as a reference our clock, what does it look like? And here is the same diagram, but with the clock signal in the middle taken as a reference. So you can see that the clock plus signal is now shifted 10 nanoseconds plus or minus 2.5 from this reference. And then the other 2, clock minus and clock in, are shifted 10 plus or minus 2.5 for clock minus, and then 20 plus or minus 5 nanoseconds for clock in. So now that we have those 3 additional phases compared to the clock, we're going to be able to use them. And specifically, we'll keep using the clock plus signal in order to generate the latching and the read signal. And we'll use the clock in signal in order to generate the write pulse, because it has just the right amount of shift to the left in order for the write pulse to work properly. There is one problem that we have to solve with this, and that is up until now we were using the inverse of the clock in our logic, and as well we were using the inverse of clock plus, but we have no way to generate inverted clocks now, at least not in a precise fashion. And so we need to update our logic to use positive clocks. So let's go into digital, and we'll see which transformations we have to do to our logic in order to work with positive clocks. All right, so I started by porting into digital our data bus demultiplexing logic. So we've built this in one of the earliest video, and I didn't do a digital simulation of it yet. So this is just a direct port of the schematic that we have. And I've added a test with the right truth table. So I'm going to copy this and create a new document, and this document is going to contain all the logic. So I'm going to save this one as glue.dig. And the reason I want to do this is because I want to be able to optimize taking into account all the available gates for the whole glue module. I'm also going to take our read and write pulse circuit and add it to the glue module. And as you can see, you can have multiple tests per sheet, and each test can only test a subset of the circuit. So all the inputs don't have to be specified everywhere. It will just use those and ignore the ones that are not specified. Of course, we have to merge the inputs of the two. So I will report all the inputs and add tunnels. And tunnels are digital labels. There we go. Now signals are going to travel between all the tunnels that have the same name, and we have only a single set of inputs in this module. And so now we're going to be able to run the tests. And as you can see, each test element gets its own tab, and you can see that the tests are still passing. So compared to our glue logic here, I will be ignoring the ready registered signal. I'm just going to call this ready, but we have to port this one as well in order to have all our logic gates in the same place, as well as these two. So I needed to add a second input called ready in order to simulate this circuit. And of course, the rest of our logic works with ready in. So let me change this everywhere, including in the tests. And now we can write a test for this sub-circuit. There we go. And now we have two more gates. We have an OR gate and an AND gate. But these are going to be VA in sync. There you go. This is everything. Okay, so we need to remove all the inverters that are in front of the clock here. We want our logic to now use a positive clock. And actually, let me implement the clock in circuit. So this in digital is a delay element. So I will add propagation delay to a signal. So if we take clock in here and add 3 of them, we can get clock minus, clock, and clock plus. Of course, now we have to rename clock to clock in here. All right. There we go. So we want to remove all the inverters that are in front of the clock signals, because we can't invert the clock in a precise way here. So let's do it. So in this first circuit, let's use De Morgan's law to invert those inputs. So if we replace the AND gate with a NOR gate, which we have to make it 3 inputs, then we can remove this one, and instead add it to the ready input. And we have to do the same here. There we go. And let's do the same in this circuit. We can replace the NAND with an OR. We have to move the inverter to the ready in signal, and then this works. Oh, and actually I forgot that we had made an update to this. So this inverter is a NAND gate. Here we have a 3 input NAND with the inverted clock plus. Okay, so let's start again. So we have to replace this one with a 3 input OR, and we can move the inverter to the ready in signal. So of course this doesn't work very well because we don't have 3 input NORs or 3 input ORs that are fast. There is one more change I need to make though, and that is we need to shift the right signal to the left. And so remember we said we wanted to trigger before 10 nanoseconds after the falling edge of the clock, but it can take up to 25 nanoseconds to trigger. So we have to shift the signal from the clock 15 nanoseconds. And if we look at our new timing diagram, if we use the clock in signal For this, there is 15 nanoseconds here at the worst case. And so this should work. So we're going to use the clock in signal to shift the write pulse. So this one is only going to be used for the read pulse. So we can move it here. And then instead of using this for the write pulse, we can use our clock in signal. And this is going to shift it by the right amount. So let's zoom in on this part of the circuit. As we know, we don't have any 3-input NOR gates that are fast. We have the 7427, but it only exists in the HC family, which is too slow. So we have to change this to 2-input gates. And the way to do that is to add an OR in front. So we could do it like that. However, the edge of the clock is significant here. This is the latch enable signal. And if we look at the timing diagram of the latch, we know that the latch enable signal has to happen at most 8 nanoseconds after the rising edge of the clock. So we need this to be fast. So instead of sending the clock to this OR gate and then to the NOR, I'll send the other one. There we go. This one we can make a 2-input NOR, no problem. So this works. Then here we have to do the same and add an OR gate in front. And similarly, I'll send the clock in the second OR gate. Now we already have the OR of clock plus and the inverse already in here, so we don't have to compute it again here. Similarly, we already have the inverse of bus enable here. Okay, so now if I count my gates, I have 1, 2, 3, 4, 5 OR gates. So we have one too much, and this means we have 3 spares. I have 1, 2 NO gates, so I have 2 spares. I have 1, 2, 3, 4 NAND gates, so I don't have any spares. I have 2 3-input NANDs, so I have 1 spare of those. And then I have 3 spare AND gates. So that's not really efficient. Let's see what we can do in order to improve this. So it would be nice to remove this AND gate, and I don't actually need this signal to be fast. So I can do it like this. This way I can remove the AND gate. Actually, I can use the NAND gate here if I invert the inputs. So I can replace this with a OR gate, and I can take bus enable directly. Now this gate is redundant, and we can remove an OR gate, and we have a spare NOR. And I think what I'm going to do with the spare NOR is just generate the inverted clock again. There we go. Let's go into KiCad and implement this new circuit. Okay, so let's start with the data bus demultiplexing circuit. The bus enable line doesn't change. Here we take one of the 3-input NANDs. And here, those go away. And we have to add a 74 LS02. That's going to be our 4 NOR gates. This one goes away. The AC11, we don't use it anymore. Okay, so we have the NOR of the clock, and then on the OR. There we go, that's the first side, and then this also goes here. And the inverse of ready reg we can get at the flip-flop. Then the sync signal is using 2 NOR gates. And finally, for the read and write pulse, we have to disconnect this one. So for the write pulse, we have the OR of clock in and a ready reg. And the inverse of ready reg. This goes into a 3-input NAND. And then on the other side, we have the OR of the clock. And the signal over here. And we can remove everything here. There we go. And our clock generation can go here. And here we generate the inverted clock. Okay, so I feel like the complexity of this module has increased quite a bit, but still we're able to make efficient use of all our gates. So it shouldn't be a massive change in the bill of materials. So at least that's a consolation. I do have to update my inputs and outputs now because the clock and the inverted clock are going to be outputs. And we have a new input that is clock in. There we go. Let me update the top level. So I need some space. Okay, and now from the clock, we're not going to take the inverted clock anymore, and we're just going to take the positive clock, and that's going to be our clock in. Okay, I just noticed an error here. This shouldn't be a NOR, it should be an AND. And I guess we can take it from here and use this one for the inversion. One last thing I want to do is replace the 74AHC367. Because we have switched from the AC10 here to the AHC32, this one is just a tad slower, and the 74AHC125 is just a tad faster. So this will restore the 25 nanosecond propagation delay. So we can remove this one and add the 74AHC125. So this one is going to have 5 units, and we can use the first unit to drive the read, and the second unit to drive the write. There we go, and then we connect the rest of the units to VCC. Okay, so this is starting to get cramped. So let's update our timing diagrams with the new circuit. Here is the timing diagram of the bank address latch before the change. And here's the timing diagram after the change. Here's the timing diagram of the buffer before the change. And here's the timing diagram of the buffer after the change. So here is the timing diagram of the ROM before the change. And here is the timing diagram after the change. So let's do the RAM now. So this is the timing diagram of the RAM before the change. And this is the timing diagram after the change. As you can see, we still have plenty of margin for this RAM chip. Now let's do the write cycle. So here is the timing diagram before the change. And here is the timing diagram after the change. So a number of things have changed here. I've switched to using the clock in input, which is the farthest shifted to the left compared to the clock. It's shifted by 20 nanoseconds plus or minus 5. And by feeding this into the write pulse, I'm able to ensure that the write pulse finishes at the 10 nanosecond mark, which is where the write recovery and the data hold timings say that we have to finish it, because the address can start changing here. So we're now able to meet this requirement. And the only thing it did is shift the time where the data has to be valid way before the falling edge of the clock. But as you can see, we are still meeting this timing here because we have quite a bit of margin on the write buffer output. This was the last timing diagram that I wanted to look at, and also the one I wanted to fix. And so it seems that our new circuit meets all the requirements needed for the glue logic to function correctly. The one little detail that is not working with the new circuit is the latching. As you can see, the latch-enabled circuit can take up to 8.5 nanoseconds in the worst case to trigger, and we need to hold the bank address for 2 nanoseconds after that. So that's longer than the 10 nanoseconds that we have. However, if we look at the datasheet of the 74AHC02 NOR gate in the switching characteristics at 5 volts, So you can see I've used the worst case here of 1 to 8.5, but that's for a load capacitance of 50 picofarad. However, I think we may be able to get away with the 15 picofarad capacitance because there's only ever going to be one gate connected to this output. And if we look at the datasheet of the 74AC563, which is the latch that we're using, the input capacitance is typically 4.5 picofarads. So we should be fine using the value for 15 picofarads here, which is 1 to 6.5. So this is the timing diagram with 8.5. And this is the timing diagram with 6.5, and I've added the comment here that this is with a single load of gates with a line capacitance of 15 picofarads. And so this fixes our issue here. Okay, so this is our breadboard where we left off the last time. And so I will be redrawing this whole board with the new glue logic circuit. Let me pull everything out and then we can get started. So the first thing we have to update is this connector here. We don't need the inverted clock anymore. So we can remove it from the connector. That's this wire here. And actually what I'm gonna put in its place is a ground wire. So there we go. And then this can go straight into the DS1035. This is the reset wire. And the clock goes into pin 1. Then pin 7 and 2 are connected. And also pin 6 and 3. Then we go into the 74HC74. We have a 10K pull-up on pin 12. So that is our ready input, and it goes to the debug module here on pin 6 of the buffer. Now the clock goes to pin 11 of the flip-flop, and the clock is on pin 6 of the DS1035. And the clock also goes up to the CPU. Pin 10 and 13 of the flip-flop go to VCC. As well as pin 1, 2, 3, and 4. Then we go into the NAND gate. So pin 9 of the flip-flop goes through a diode to pin 13 of the NAND gate. Pin 12 and 13 are connected together, and there's a 1K pull-up. And that's ready. So ready goes to the CPU on pin 2. Then pin 10 and 11 are connected together on the NAND. And one of them goes to pin 8 of the flip-flop. And this is our wait signal. And wait goes to pin 9 of the buffer in the debug module. Then we need VDA and VPA to pin 1 of the NAND. So that is pin 7 and pin 39 of the CPU. And then pin 3, 4, and 5 are connected together. And pin 6 is the sync signal that goes to pin 3 of the buffer. Sorry, that goes to pin 1 of the inverter here. Then we go into the 74HC32, which is the OR gate. And I'll take VDA and VPA through the first inputs here. And that gives us VA, which goes to pin 3 of the inverter here. Okay, so then we need the clock input going to one of the inputs of the OR gate here, as well as the inverse of ready reg, which we can get from here. Then on pin 12, we also need the inverse of ready reg. And on pin 13, we need clock plus, which is pin 5 of the DS1035. And then the output of this goes to the next gate, along with the clock. Then we go into the NOR gate, 74HC02. Along with the clock. And this gives us the latch enable. So the NOR gate we use to invert bus enable, which goes to pin 8 and 9 of the NOR gate. Actually, I'm going to put it at the bottom, on pin 4 and 5. And we also use it to generate the inverse of the clock. And the inverse of read-write, which we can get at the CPU on pin 34. Then we go into the 74AC10. On pin 10 and 11, we have bus enable. And on pin 8 is the output enable of the buffer, which is pin 19, so that's this one here. On pin 1, we come from the OR gate. On pin 2, we have VA, which also comes from the OR gate. Pin 13 is read-write. And pin 12 is the output. Then on pin 3, we also have VA. Pin 4, we have the inverse of read-write. And pin 5 comes from the OR gate. And pin 6 goes to the buffer. Finally, we have the buffer, 74AHC125. Pin 8 to 13 can go to VCC. No, actually, only pin 9, 10, 12, and 13. So pin 2 comes from pin 12 of the AC10. And pin 5 comes from pin 6. And then pin 1 and 4 are connected together. And they come from the output of the NOR gate, which is inverting bus enable, pin number 6 here. Okay, and we have to add 10K pull-ups on read and write. It's pin 3 and 6. I believe this is everything. So let's connect back the sync pin, which is here on the monitor, the read write, and VA, which is here. And then this is read, that's pin 3 of the buffer. And this is write, pin number 6. Okay, I believe this is everything. Let's turn on the power. And something's wrong with the buffer. We have no data here. Okay, connected this to VCC. Oh, and there's another unconnected pin here on the latch. So this goes to the inverse of bus enable. Okay, I see the problem here. I just inverted the output and the input. Okay, so I think I fixed it. As you can see, the CPU is now running. I had inverted the two upper outputs of the NOR gate here with their inputs. And I think that created a short, and it may have damaged some of the inputs of the NOR gate here. What just happened? I'm having an issue with my wait signal. And should be ready reg, not the inverse of ready reg. As I was saying, I may have damaged some of the inputs of the NOR gate here because when I try to connect the first one, it just creates a short, so yeah. But at least the CPU is working. So let me clean everything up and we can conclude the video. Okay, so in this video we've reworked our glue logic so that the read and the write signal take into account all the control signals of the CPU and so that the timing works in all cases. So I think that was the last major glue logic / timing project. Now I think the structure is pretty good. The next projects are going to be adding some IO and some extended RAM, and so we're going to start being able to do more things with the CPU, so that's pretty exciting. One other project I'm looking at is moving some of the pieces to PCBs, because honestly this wiring is not the greatest and it's starting to annoy me a little bit, not to mention the instability issue we still have with the data bus. I'm thinking I'm going to go with a backplane solution, and currently I'm looking at various types of connectors for the backplane. It's looking like I will go with PCI Express connectors, which have pretty good signal integrity and a good number of connections. So if you have any ideas about backplanes or any suggestions of things I should keep in mind when designing them, I'm all ears. Let me know in the comments. So I hope you enjoyed this one. I know it was a bit theoretical and I went into a lot of detail on the timings, but I think it's quite useful and now we have a good solution. So let me know in the comments if you've got any questions or feedback. And I hope to see you in the next one. Goodbye.